Yeah, I would first like to thank the organizers and specifically Ratul for organizing this and giving him an opportunity to speak here. So, I mean, it should be evident from the title, this has not much to do in the way of interfaces. But I'm going to talk about a work that I do in the group of Björnhof in Austria on work we have been doing for the past decade on understanding transition to turbulence in wall-bounded shear flows. I will present one result on Taylor curve, but otherwise I will mainly stick to pipe flow in this talk. Yeah, so the background. So in wall-bounded shear flows, turbulence often arises even though at Reynolds number values where the laminar flow is still linearly stable. And so in spatially extended systems, one has spatio-temporal intermittency, where you have laminar and turbulent regions that coexist and fluctuate in space and time. So these are examples from Taylor curve, plane Posey flow, and pipe flow. In pipe flow, these turbulent structures are called puffs, and they usually advect with roughly the bulk velocity. Now, one could ask a question dating back to Reynolds as to what is the critical, because it doesn't have a linear instability, is there a critical Reynolds number for the transition to sustain turbulence? And after decades of conflicting evidence and confusing results, the current understanding is as follows, that there are two competing processes. So simply put, once a puff is created, it can exist for a pretty long time with no change in the mean properties, and suddenly it can either decay or split into two. It turns out these both processes are memoryless or Poisson processes, so the probability does not change with time. This of course means that the probability for a puff not to split or not to decay after a time t exponentially decreases with time, with a typical time scale tau, which is a function of Reynolds number. Now this functional dependence of tau on Reynolds number was obtained experimentally, and this is the graph. So on the left we have the curve for decay, time before decay. On the right we have the curve for time before splitting. The intersection point is roughly at 2040. So if you start with a pipe full of puffs, then to the left of this point, decays will overweigh splittings and you will eventually return to laminar, whereas to the right of this point, you will sustain turbulence. So this is the first answer to the critical number problem in pipe flow. I should mention that the time scales increase very rapidly and decrease very rapidly here. In fact, a double exponential fit is a very good fit to the data. A couple of points about this. The first is that because of the nature of the argument, this critical point is only defined in the thermodynamic limit of a very large system with very large number of puffs. And the second is the large time scales near the critical point. So this is around 10 raised to 7 advective time units, which means in a 10 millimeter pipe, a puff would exist for around a week and travel around 100 kilometers before it splits or decays. However, okay, in spite of this progress, no interactions are included in this picture, so we don't know how it shifts the critical point, and there is no information on the nature of the transition. So here we use framework of phase transition from statistical mechanics to try and understand some aspects of this transition. Now I'm sure many of you are familiar with phase transitions, but given the diverse background, I thought there is no harm in going through a few salient points of phase transitions. A phase transition occurs when a substance changes from one phase to another, say a liquid to vapor or paramagnetic to ferromagnetic, and is accompanied by some non-analyticity in some relevant quantity. For the purpose of this talk, it will be the order parameter, which is some quantity which is 0 in one phase and some finite value in the other phase. So for example, this could be the difference in density of vapor and liquid, or the magnetization, or in the case of fluids, it could be the turbulent fraction. So if the order parameter is discontinuous, we call it a first order transition. And if it is continuous but discontinuous in the derivative, it's called a second order transition. Now a second order transition exhibits universal behavior in which very diverse systems can exhibit the same scaling. We'll see how this comes about. For example, a quick look at the Ising model, which is a very simple model of phase transitions in equilibrium systems. So this tries to model the way a paramagnetic substance, as you cool it down, it finally attains a magnetic field and becomes ferromagnetic at a critical point. So this, for 2D, you have a system of a lattice with magnetic moments either pointing down or up, and there are two competing effects. Temperature, which tries to randomize the spins, the magnetic moments, and magnetic interaction between neighbors, which tries to point them in the same direction. At high temperatures, temperature wins and you have very small clusters of either orientation and no net magnetic field. But as you cool it down, larger clusters start to form till at a critical point one orientation just begins to win over and you have a smooth increase in the magnetic field. Now the crucial point is that at criticality, the correlation line diverges. This is a measure of how fluctuations in one part of the system relate to fluctuations farther away, and the fact that you have this large scale organization means that the microscopic details don't matter and very different systems can show similar universal scaling behavior close to the critical point. Now one can play the same game in non-equilibrium systems where the simplest model of a phase transition is directed percolation. So here I consider a model of bond directed percolation where we are trying to model percolation of fluid through a porous medium. So here it's very simple. You have a set of lattice points with bonds connecting them. The bonds are either open with a probability P or closed otherwise. And one could ask the question, at a given probability, what does a fluid percolate through an infinitely long lattice? Now, instead of the static picture, one could imagine that this is actually the time evolution of the first lattice row down in time. So we imagine this row with one occupied lattice and we could time evolve it and get exactly the same picture. And I hope the analogy to fluid flow is very clear. The wet sides are the turbulent puffs and the non-occupied sides are the laminar flow. The crucial thing in the analogy is that a side cannot become wet on its own but only by contamination from the neighbor, just as what happens in pipe flow. A puff can decay spontaneously but it can only become, a region can become turbulent only from an existing puff. And the question of sustained turbulence in this sense means if you start with some active sites, does it remain active till time tends to infinity? And as expected, this shows a phase transition from a percolating to a non-percolating phase as we decrease the probability. And the order parameter, which is the proportion of wet sites, goes continuously to 0. Because this is a continuous phase transition, one has universal behavior with many different models exhibiting the same scaling. In particular, Pomo proposed in the 80s that all systems spatiotemporal intermittency will exhibit the same behavior in the universality class of directed percolation. But in spite of a lot of efforts, the first evidence for this in experiments was found only in 2007 and not in a classical fluid system. This was done in liquid crystals. So before I go to our work, I would like to discuss some of the exponents that we will use. So one is the proportion of active sites or turbulent fraction in the steady state, which scales with the exponent beta from the distance from the critical point. The other is the typical size of laminar gaps in space, which diverges as you come to the critical point. The typical size diverges, but at critical you no longer have a typical size. You have a scale free behavior or power law behavior with an exponent here, and you can do the same thing with gaps in the temporal dimension. Now the experiment that we want to do, I will just focus on these three exponents because there are truly only three independent ones. One can define many more. The proportion of active sites or turbulent fraction and the distribution of laminar gaps in space and time at critical. So the experiment is very simple. What we want to do ideally is take a set of puffs in a pipe, follow them long enough, do this for different Reynolds numbers and see if it agrees with the predictions of directed percolation. A couple of talks ago somebody mentioned that the devil is in the details. So I will spare you all the details here, but this setup has been evolving over almost 7-8 years, and right now as it stands, we have a pipe which is 10,000 diameters long, where the temperature can be controlled to almost 1/100th of a degree, and a Reynolds number control of better than ±1 for arbitrary long periods of time. So what we do is we can perturb the flow here, and there are two pressure sensors. As a puff passes them, you get spikes in the signal. So the main challenge is how do you follow them for long enough times when you have advection. So the way we do this is as follows. As puffs are going down and cross this sensor and about to exit, we make another puff at the entrance. So that, and this puff then when it comes to the pressure sensor S1, we can check that we are reproducing the pattern at the exit at the entrance. Now, so in some sense, it's a periodic pipe. Now why this works is because all puffs are statistically identical, and moreover the decay and splitting processes are memoryless. So this should not change the statistical properties of the train of puffs under consideration, and we can then follow them for as long as we want to check what happens. So here I present results of the time evolution of the turbulent fraction starting from different initial conditions for different Reynolds numbers, and we can see that they all converge to the same mean turbulent fraction. We also tried this in a completely different pipe with a different diameter with a different perturbation mechanism, and it gives the same average even though it fluctuates more because the pipe is shorter non-dimensionally. After having verified this, we then go ahead to measure the turbulent fraction at various Reynolds numbers, and this is what we get. I have marked this point in red because the fluctuations were so huge here that we are not even sure if it converged, and for now I will treat it as an outlier. But now, does this fit the directed percolation exponent or not? Well, we are not so good here because this is not actually a fit. This is just the expected exponent which I forced to go through the first 5 points, and as you can see, we need a lot more points in this area because you have two fitting parameters, the constant of proportionality and the critical point. So unless you have a lot more points in this area, you cannot do a good fitting and extract the exponent unambiguously. But the problem is that this measurement, for example, is a continuous runtime of 2 months, and so times diverge near the critical point, so we are going to be in trouble here. Plus, the control in Reynolds that you need here is of the order of 0.2 or better. This would mean a temperature which I need to be better than almost 1 in 1000. So this is not clearly feasible, and maybe you need a longer pipe to avoid fluctuations here. What about the laminar gap distributions? So here I show distributions a little far away from critical at 2047 and close to critical at 2040. Here is a semi-log plot and here is a log-log plot for the same two things, and the dotted line is the expected dp exponent. As you can see, it's clearly exponential far away from critical, and at critical it shows kind of a power law behavior and matches the exponent reasonably well, but you can't say much because this scaling is less than an order in magnitude. So you need at least 2 orders, which means my pipe has to be at least 1 order of magnitude longer, which is a few hundred meters long. So again, we have a problem here. So I would say that the data is not inconsistent with dp, but doesn't confirm it either. For the moment, I leave the pipe aside and present some more cheerful results from Taylor-Couette flow. So this was the first experiment to unambiguously show dp scaling in a fluid system. So what we did was we took Taylor-Couette system, but we shortened the axial direction so that the spatio-temporal intermittency is essentially one-dimensional, and the gap was just 250 microns, so we were able to achieve a huge aspect ratio. And then we run the system, and this is how the space-time plots look. So on the right, we have experiments below, at and above critical. On the left, you have the directed percolation model from bond percolation, and they look quite similar. But even more precisely, we could extract all the 3 exponents which I talked about quite precisely. And then we, in the group, Lucas was able to go on and show that in a proper 2-dimensional Couette system, also all the exponents now corresponding to 2D directed percolation were recovered. So what do we do about the pipe? This is joint work with these people. So what we decided was something similar to a percolation model. You have some microscopic rules, like say the probability of the bond, and then you simulate this on a large lattice to see what's the large scale structures that emerge. So same way, we decided to use experiments to extract microscopic rules on the scale of a puff, and then do some simple model simulation to extract the large scale features. And we also used a discrete model and field theory calculations to check the robustness of our conclusions. But I will mainly focus on the first part. So what are these microscopic rules? We identified 4 of them, and we think that's all. Let's see what we get. So the first is puff repulsion. When 2 puffs are very close to each other, because of the modification of the profile, the downstream puff actually travels faster, and eventually at around 100 meters separation, it goes with the speed of an isolated puff. So we measured this speed for different Reynolds numbers as a function of distance, and we were able to collapse it to a universal curve with the isolated puff speed modified by an exponentially decaying. The next is again the same thing. If there are 2 puffs close to each other, the puff downstream tends to decay faster, and the puff upstream is inhibited in its splitting. So we were able to show that for all distances, the decay process and splitting process are still memoryless, and we can extract time scales which we fit with exactly a double exponential function as before, but now the coefficients depend on the single puff coefficient plus an exponentially decaying part with the same length scale as for the puff repulsion. And finally, by measuring the fluctuations in the arrival time at different distances in the pipe, we were able to show that in addition to the mean advection, you also have a diffusive component to the puff, and we were able to get the diffusion coefficient as a function of Reynolds number, but we just use a constant value because in this range where we are concerned, it doesn't change too much. And we put all this into a simple model where puffs are treated as point particles, and they are evolved according to the microscopic rules of repulsion, puff separation, dependent splitting and decay, and diffusion. This was done in a domain which is 2 orders of magnitude bigger than the experiment, with periodic boundary conditions and accelerated GPU computation. And here are the results. So the orangish markers are the experimental data, and this is the blue ones are the from the model. As you can see, they fitted much better than what even we expected, and this gives me more confidence that this point is an outlier. But now we are able to go closer to the critical point, and this black line that you see here in the inset, which is now a log plot, is the correct scaling function for dp, and it matches it quite well to around 2 orders of magnitude. But in actual Reynolds number, this is just 1 in Reynolds. One of the reasons why the scaling range is probably so small is what happens is that in the percolation, it's the probabilities which matter, but the probabilities depend on time, and the time depends super exponentially on the Reynolds number. So a finite change in probability is achievable by a very, very small change in the Reynolds, which is why in terms of Reynolds which we use, the scaling range is so small. The laminar gaps in space and time are quite nicely captured here in almost 2 orders of magnitude. Yeah, I should also point out that these last points were integrated for around 10 raised to 12 time units in the model, which corresponds to several decades at each Reynolds number in the experiment. Finally, I want to, these are space-time plots from the experiment, which show this kind of jammed phases where you have short range order in the puffs. You have them far away from critical, but you also have it quite close to critical as well, even though it's much reduced. And we are still not, we have not studied this deeply enough, but just as a comparison, looks a little less resolved than I thought. But so here we use a simple criterion to discriminate these regions of short range order from the in-between regions, and this is the model and this is the experiment, and we can see first of all that the jamming increases as we go to higher Reynolds numbers, and we expect eventually to reach some kind of crystalline state, let's say, but also the qualitative agreement between the two is excellent. And finally, we were able to use a model which is also discrete in space so that we can accelerate the computation and check that the model is, the DP transition is robust to changes in splitting and decay rates. So wherever we go from a low puff density to a high puff density, we get a DP transition. This black line here is actually the path followed in the experiments and in the model. So that's as far as the results. So combination of experiments and modeling shows evidence for DP transition in pipe flow. But now I would like to present some future outlook, which is we are still looking for more direct evidence where you don't have to use a model, because that's always the question people ask, how do you know you didn't miss something in the model? And what are the conditions for DP violated in some other systems? Because we don't have a theory for non-equilibrium phase transition, so you really don't know what are the conditions for universality or not. Can you even be kicked out of the DP class or even go to a discontinuous transition? So I will not go into detail, but I'll just present at a glance some quick results. So we found out that if you have a small curvature in the pipe, very, very small, this is a curvature ratio, then you get exactly the same behavior as in a pipe, but with the time scales which are 4 orders of magnitude smaller. So this is comparable to what is there in Taylor-Couette, and we hope that by using such a pipe and the periodic boundary conditions, we can actually get direct evidence for the directed percolation exponents. Another is the case of channel flow, where stripes do decay, but it turns out if you look at these red dots that all you have to focus on, these are experimental data. As compared to the gray markers which are pipe data, you can clearly see the non-exponential behavior of these stripes in decay. It turns out that same is true for splitting. So does this have an impact on the transition? Does it throw it out of DP or not? We don't know yet. And finally, sorry about this, I have no idea how this happened, but this is a Linux system, so it does crazy things sometimes, and OpenOffice. But anyway, the point is, I'll just orally say this. So we found out that if you use body forcing in pipe flow, we use 2 artificial body forcings. One is a plug forcing and another is parabolic forcing. We did experiments in a curved pipe where you have the centrifugal force, and in a heated buoyant pipe. And all these cases we find that the region of spatio-temporal instabilities is orders of magnitude smaller than in pipe flow. And so we don't know whether it is DP close to the transition point, but in one case, the parabolic forcing, the region of discontinuity is definitely, the region of going from 0 to 1 turbulent fraction is almost less than 0.1 in Reynolds. So maybe we are even looking at a discontinuous transition, but these are questions for the future. So with this, I thank you, and I will be happy to answer any questions.
Long live India and France friendship.